Here's another example. Again, I've taken this from your textbook. It's in problem number 32 in 15.3. We're given this lovely integral. Okay, I'm not thrilled about it, the way it looks. I recognize that that would just be r in polar coordinates, because when we integrate, r has to be non-negative, so that it is the positive square root of x squared plus y squared. I also see here this limit of integration involves a square root and some squares. Now, it's not quite as nice as what I generally see when I've got a circle centered at the origin. But anytime I see a square root, some subtraction, and some squares, I'm suspicious we've got circles. So let's explore. So I want to take a look at what this region looks like. I know x is varying from 0 to 2. Okay, that's this. Y is varying from 0, so I'm going to have a bottom boundary of the x-axis, to that top boundary, which is y equals root 2x minus x squared. Again, I'm going to square both sides. So y squared plus x squared is equal to 2x, and y is bigger than or equal to 0. When I square both sides, I don't want to lose the information that y was not negative. Okay. All right. Well, that's y squared plus x squared minus 2x is equal to 0. I think that's going to be a circle. In rectangular coordinates, I would need to complete the square to put that into standard form. And that would be one option that I could do. The other thing I could do, though, is I could switch this thing to polar coordinates. Okay? I'm going to do that, and if I were completing the square, I would move the two x's over. I think if I'm going to convert to polar coordinates, I'm going to just keep it like this. Y squared plus x squared is r squared, and 2x is 2r cosine of theta. Okay. Now, ideally what I want, if I'm trying to describe a curve, is I want to have r equal something. Okay. So what I kind of want to do, if I can, is divide both sides by r. Because if we divide by r, I'm going to get just r is equal to 2 cosine theta, and I recognize that as a circle. We'll review that in a moment. Okay, but that's kind of cool. But now, I'm going to just call this equation 1, and I'm going to call this equation 2. They are obviously not the same, because r equals 0 is a solution to this one regardless of what theta is. Okay. But if I were to say, let's let r be 0 and theta be 0, that's not a solution, because then this becomes 0 equals 2, which we know to be false. Okay. So algebraically, these have different solutions. But what's very interesting is that in polar coordinates, if r is 0, we are talking about 1 point. That's very unique. If r is 1, we're talking about infinitely many points, because it's every point on the unit circle. If r is 0, we are talking about 1 point, and that's the origin. So the origin is clearly on this graph, because if I plug in 0 for r, it makes the equation true. The question is the origin on this graph as well? If so, even though they're algebraically different, they would have the same graph. So is there a solution that would put the origin on this graph? R would be 0, yes. If theta was pi over 2, this would be equal to 0, and then r would equal 0. Okay. So equation 1 and 2 are equivalent if r does not equal 0. The origin, which is what we get when r is 0, is on both graphs. So they are graphically equivalent. Very, very cool. Okay, so I've got r equals 2 cosine theta is going to be my upper limit of integration for y. So that's going to be my top boundary. So let's see if we can see what that looks like. Okay. There aren't a whole lot of curves that I expect you to just know in polar coordinates, but you should know the following. You should know r equals cosine theta, and this is just a multiple of that, and r equals sine of theta. Okay. If we forget what these are like, we can always create a quick table of values for theta and r. Okay, and then I'm going to graph my answer here. If theta is 0, cosine of 0 would be 1. So when theta is 0, we're at 1. So we're at the point 1, 0 on the x-axis. When theta is equal to pi over 2, which is my next quadrantal angle, cosine is 0, so we would be here. And as theta varies from 0 to pi over 2, what is r doing? Well, it's decreasing. Okay. So as we rotate, r is getting smaller. Turns out we're drawing the top half of a circle, like so. And then when we go to pi, by the time cosine of theta is pi, r is -1. If this is pi, that's the positive direction. The negative direction points in the opposite direction. We're going to come around and complete this part of the circle. So r equals cosine theta is a circle whose diameter is 1. That makes the radius 1/2. And it's centered on the x-axis. Not centered at the origin, though, because it passes through the origin. Okay. All right. Now, my curve here was r equals 2 cosine theta. And that's going to be just this circle twice as big. We've stretched everything by a factor of 2. We said we only wanted the part of that where our y values were positive, so we're essentially getting the top half of that circle so that the region over which we're integrating is that disk. One big word of caution here, notice as I was tracing this, between 0 and pi over 2, my r values were positive. Between pi over 2 and pi, my r values were negative, though. When we're integrating, we need to make sure that our r values are positive. So when you have r is a function of theta as your boundary curve, you're going to need to check to make sure that that function is always positive. If I were integrating over this whole disk, rather than integrating from 0 to pi, over which I'd have some negative r values, I would integrate from negative pi over 2 to positive pi over 2. Because from negative pi over 2 to 0, I also draw the bottom half of this circle, but I draw it with positive r values. Okay. There are times, I will just warn you, that you can use r equals cosine theta. You can set it up for your limits of integration. Your r value is negative and you get the same answer, the right answer anyway. That's because you're essentially making two mistakes. You're letting r be negative, and then we always set up our integration so that we integrate from smallest to biggest. But if you set it up so that you integrate from biggest to smallest, that reverses the sign of things. Sometimes that does happen, but it doesn't happen every single time. So you must set up all of your integrals so that your r values are always positive. Okay, r equals sine theta, just to review that one really quickly. That's just a circle of diameter 1 that again passes through the origin but is centered on the positive y-axis. And if I had a positive multiple of that, it would just make it bigger or smaller. A negative multiple of it would just push it down to below the x-axis. Okay, very cool. So we've got our region figured out. Let's see now if we can't do our integral. Okay, so I want to set up my limits of integration. This is just the top half of the disk, and we just saw that that's going to be as theta varies from 0 to pi over 2. Now, as I look at that, I've just drawn in some constant theta rays here. I want to see, when I'm holding theta fixed, r varies from what to what? And I can see r is varying from 0 to the r value on that circle. So it's going to be varying from 0 to 2 cosine of theta. So I've got a functional limit of integration here. And again, I can double check that on that interval, this is going to be positive. Okay, then we're integrating this, which is just r. Of course, that's just dA, but dA is r dr d theta. So when I combine the two r's, we end up integrating from 0 to pi over 2, from 0 to 2 cosine of theta, r squared dr d theta. Excellent. So I'm going to get the integral from 0 to pi over 2, r cubed over 3, evaluated between 2 cosine theta and 0, and then we still have to integrate that with respect to theta. Beautiful. Integral from 0 to pi over 2, 8 cosine cubed theta over 3 minus 0 d theta. Okay, so I'm going to factor out the 8/3. So I've got 8/3 integral from 0 to pi over 2. And then I want to remember how to integrate an odd power of cosine. Remember, the trick is to break that up into cosine squared theta times cosine of theta d theta. That's still cosine cubed. But now I can rewrite that even power in terms of signs. So I can say this is 8/3, the integral from 0 to pi over 2. Cosine squared is 1 minus sine squared of theta, and then times cosine theta d theta. You can see this cosine theta that I separated out is all set to be absorbed into my du, because I'm going to now let u equal sine of theta, so that du is cosine of theta d theta. And so, I think that's going to give me enough space to finish this one up. So just working in this section of the board to finish this up. If I do that u substitution, I'm going to have 8/3 the integral from the u value at 0 is sine of 0, that's still 0. Sine of pi over 2 is 1. So I'm going from 0 to 1. And then this becomes 1 minus u squared, and this is just my du. So that's 8/3 times u minus u cubed over 3, evaluated between 1 and 0. That's 8/3 times 1 minus 1/3 minus 0. That's 8/3 times 2/3. That is 16/9. And there was much rejoicing.